previous lectures, we have mostly been setting the foundation, okay? So I gave you the foundation of basically all the Python packages that we'll be using, the Python software libraries such as NumPy, SciPy, scikit-learn. All those were discussed, I would say, fairly in the abstract. That's unavoidable. I don't want to spend a lot of time going through code examples on those because ultimately the way that you will be using those libraries is in the building machine learning models for predicting material properties, okay? So, and it is my personal belief that there's no better way to do that than actually getting to the lectures where we are actually going to talk about the machine learning models and giving you the code examples and then also you practicing it in your lab number 1, okay? So today is your very first lecture on machine learning models, okay? And this will be what we are going to do for essentially the rest of the course. We are going to go through all the different types of machine learning models that are out there. I'm going to talk about their fundamental differences, but mostly I'm actually going to talk about where they are similar, right? And one of the things that you will notice when you go through this entire course is that most of the principles that you learn about machine learning model are universally applicable, okay? So things like whether you need to split into test and training set, whether you need to do cross-validation, what is overtraining, what is undertraining, all those things are things that you need to take into account no matter what kind of machine learning model you are using, okay? So with that in mind, our very, very first lecture, I'm going to introduce to you something that you are probably already familiar with, okay? And those are linear methods, right? The reason why I do this is because since you already understand this, or you may have used it in the past, for example, you have fitted a linear regression line in one of your high school labs or even during your research, you already understand at least some of the basic mathematics involved. And using linear methods is a good way to actually then talk about best practices and then talk about how we can actually extend those linear methods beyond that simple linear regression line that you have already done in your high school, okay? All right. So this is actually where we'll spend a lot of time on formalism, methods, and best practices, okay? Once we actually get to the other machine learning models, I will assume that you already understand all those best practices because we already touched on them in linear methods, and applying them for other machine learning models is not going to be any different, okay? I'm going to talk about concepts such as what is bias and what is variance, and then with that, we will then apply those same concepts to other machine learning models as well, okay? All right. Now, a little bit about notation. In general, I will use capital letters to denote variables, okay? So this is a very common notation that is used. Lowercase letters will actually denote observations, okay? So if I'm talking about a specific set of data, those will be denoted using lowercase variables. And then the indices, if I use dummy index j, that indicates they are different variables. And if I use dummy index I, that indicates there are different observations, okay? So observations means I have one measurement of a target, I have a second measurement of a target, those are different observations. If I have the same material, but I'm measuring different aspects of the material, things like, for example, its electronegativity and its atomic mass, those are different variables, okay? If I bold the variables, those are essentially either vectorial or matrices, okay? So again, very, very standard notation that you probably already seen in your linear algebra course. All right, so let me start with something you're familiar with, which is linear regression, okay? Now, a linear model is essentially the simplest possible model that you can have between a target and the features. Okay. Now, when we so please note the terms. Target means the thing that you want to predict. Features means the variables, the dependent variables that you are going to use to predict the target. Okay. So for instance, you may want to know the bulk modulus of be able to predict the bulk modulus of a material. The bulk modulus is then the target, and then the features can be things like, for example, the atomic mass of the atomic weight of the material, the symmetry, the lattice parameters, the melting point, and other things that information you already have. Okay, so despite the very, very simple nature of this model, it actually turns out that linear models are extremely powerful. Okay, and the reason is because that variable x of j can actually take many, many different kinds of functional forms. Okay, the x of j can be just the direct quantitative inputs. So for instance, the electronegativity. But it can also be transformations of quantitative inputs, right? So for instance, I can take the log of a variable, I can take the exponent of a variable, I can raise that variable to some power, like x squared, x3, x cubed, and I can also use basis expansions. And I'm going to touch on basis expansions at a later slide, okay? It can also be interaction between variables. So for example, it can be the multiplication between two variables, okay? And it can also be something like encoding of levels of inputs, okay? So encoding of levels of inputs can be something like your preferences, right? Your preference can be from anywhere from level 1 to level 10, and that's called an encoding of levels of inputs, okay? Now, because x of j can take on all these different forms, it doesn't mean that we are not assuming that it is always a strictly linear relationship, right? So it doesn't mean that if I use a linear form, it must be y equals to mx plus c, okay? Something like y equals to mx squared plus c, or y equals to ax squared plus bx plus c, all those are examples of linear models, okay? So, so in essence, actually, linear models are extremely powerful, right? Despite their very, very simple functional form. Okay, so this is a representation of a linear model. Okay, so you basically have your target, which is which we use y to denote. It is some function of p variables. Okay, p features. Okay, so x1 to xp, and for a linear model, you usually have an intercept. That intercept is beta 0, and then you have a coefficient in front of all those variables. Those are denoted by beta j. Okay, so this is a summation of beta j times x of j from 1 to p. Okay. Now, so when we talk a linear model, as I showed you, is an example of what is called a supervised machine learning model. Okay, so you may have heard of the term supervised machine learning models and unsupervised machine learning model. What is a supervised machine learning model? A supervised machine learning model is a model in which you actually give it both examples of targets and examples of inputs, features, and you are asking the model to learn the relationship between the input and output. Okay? So a linear model is an example of such a model. You are essentially saying, I'm giving you y, and I'm also giving you values of x, and you are supposed to learn what's the relationship between your x's and your y's. Okay. So given that, so essentially you are going to give that model some data, okay, a set of x and y, and you are going to basically figure out what are the model parameters. Okay, in the case of a linear model, those are your coefficients beta j, okay, that are essentially optimal in some sense. Okay. We are going to discuss a little bit about what optimal means. Okay, when we talk about optimal, we are essentially always talking about what is the set of coefficients that minimize some loss function. Okay, a loss function, sometimes you also hear the term cost function. Okay, they mean the same thing. And that loss function is a measurement, is a quantitative description of how good the model is, all right, or what's the error of the model, right? So basically, what you're trying to do is that I'm going to come up with some way of figuring out what is the set of beta that would minimize the error of the model, okay? Now, whenever we talk about linear regression, one of the most common way in which you try to figure out what your betas are is basically using what is called least squares regression, okay? Least squares regression just means that I'm going to define my loss function as the sum squared error given all the observations that are in my training data, okay? So what this means is that I'm going to take each of my observations y of j, I'm going to subtract out that linear formula of x of I, okay, and I'm going to square the difference between them, okay. This gives me the error between the predicted value, which is my f of x of I, and my actual observed value, which is y of I, and I'm going to square that number and I'm going to sum it up over all the observations that I have, okay. So this is called the sum of squares, okay. Now, remember, whenever we talk about machine learning model, we want to find the set of betas that will actually minimize this loss function, right? So how do we actually go about minimizing the loss function? How do we go about finding beta that minimizes the loss function? What do you do when you want to minimize a function? Calculus, anyone? Correct, okay? So to minimize my L with respect to beta naught and beta 1, what I need to do is that I'm going to take the derivative of my loss function with respect to beta naught and beta 1, and then I'm going to set them to 0, right? So that's how you find the minimum of a function, right? So if you do that, basically you can just go through the math. The math is fairly simple. It's just your standard calculus. Don't worry about derivations, okay? So this is about the only derivation that you're going to see. The only reason why I do this is just to show you how it works. But for most other machine learning models, you don't actually do a direct minimization in such a way. You actually do an analytical minimization in such a way, but rather you actually use some numerical method to do the minimization, okay? So if you take the derivative of your L with respect to beta naught, and then you set it to 0, after you manipulate the variables, you get that essentially the beta naught must be equals to the mean of y minus beta 1 times the mean of x. If you take the derivative of your loss function with respect to beta 1 and set it to 0, you essentially get that your beta 1 is given by your covariance of x and y divided by your variance of x, okay? So now, once you have, so basically your beta 1 is just a function of your x and y observations, and your beta naught is just given by the mean of y minus the beta 1 that you actually get from here, multiplied by the mean of your x, okay? So with this, we now actually have a way of finding our beta naught and beta 1, right? So if you actually do this for I started with a very simple example where I'm talking about y as a function of one independent variable, which is x1. But you can also generalize this to basically a multiple linear regression model where you essentially have a y that is dependent on p x variables, right? And for this, if you think of the observations as basically y1, y2, y3, all the way to yn, so let's say you have n observations, and you create this matrix of this vector of your coefficients, which is beta naught, beta 1 to beta p, and then you create this x matrix, which basically are just your observed x values. You have a 1 because your beta naught is actually an intercept term, Okay, so essentially that gives you a matrix multiplication where you basically have y is equals to your x matrix multiplied by your beta vector. Okay, you can verify for yourself that if you do this matrix multiplication, you essentially get a series of equations equations like this. Okay, now I'm not going to go through the derivation again, but essentially if you go, try to calculate the loss, okay, the residual sum of squares is just basically y minus x times beta transpose times y minus x times beta, okay, and this essentially is the sum of squares of your multiple linear regression model. And if you go through the same kind of derivation, you take the derivative of L with respect to your beta vector, you can essentially show that your beta is just given by x transpose x inverse multiplied by x transpose times your y observations. Okay, and that gives you basically that your predicted y is just this beta vector, this x multiplied by this beta vector, which essentially gives you this expression over here. Okay, so in linear regression, we have an analytical solution for what is the optimal beta given our observed x and y. Okay, and so this is something that can be solved quite easily, right? You are just essentially taking a matrix, you are doing a transpose or taking an inverse, and then you are just doing the multiplication. Okay, most of you should be able to code this up in MATLAB in like a few minutes. All right. Now, we are of course not going to ask you to code that. Okay, that's far too trivial a problem. But rather, I'm going to show you how you can use scikit-learn to run a multiple linear regression model. Okay. Now, this is basically a graphical representation of a multiple linear regression model with two dependent variables, right? I choose this because so that we can visualize it more easily. Essentially, when you are trying to fit a multiple linear regression model to this function of two variables, x1 and x2, basically what you're trying to do is you're trying to find this surface that essentially minimizes the distance between each point to the surface of this, to the fitted surface. Okay, so you're minimizing the square of the distance between each point to the surface. Okay, so that essentially gives you your optimal beta that actually defines this surface over here. Okay, all right. Now, very often one of the things that we have to be careful about are some of the assumptions that we make when we use use any machine learning model, right? So whenever we use multiple linear regression, we are making a few assumptions, right? The first is that all the observations are drawn independently drawn at random. Okay, so in other words, there's no correlation between any of the observations. Okay, so that's almost always assumption that we make when we use a least squares criterion. Okay, we also assume that the variance of our actual target observations is a constant, right? So in other words, that variance of y is given by some constant sigma square. So there isn't like an increasing variance with larger values of y, right? Nevertheless, this criterion is actually not very strict. In fact, you can actually design a weighted least squares method that actually accounts for this kind of if the variance of y is not constant. Okay, and because of that the variance of y is a constant, you can actually estimate the variance using this very standard estimate for the variance of a variable. Okay, all right. Now, I'm going to show you how to do multiple linear regression using scikit-learn. Okay, and this is also a useful way to show you how to actually the API of the scikit-learn code package, and just to show you also how you can predict certain properties of materials using certain features. Okay. Now, I already provided the data. Okay, that's inside the GitHub repository. The materials data that I gave you, the target that we want to predict is the bulk modulus of the elements. Okay. So in other words, I want to be able to predict what's the bulk modulus of each element from the actual, from certain other features of the element that I actually have, that I know about. Okay. So the candidate features that we are going to use for our multiple linear regression model is the melting point, the boiling point, the atomic number, the electronegativity, and the atomic radius. Okay. So all that data is in this comma separated value file. Okay. And what you see is that the first column is basically just the symbol of the element. The second column is basically our target. Our target is given is K, which is the bulk modulus. Okay. This is the bulk modulus of all the elements here. This is the MP stands for melting point. BP is boiling point. Z is the atomic number. X is the electronegativity, and R is the atomic radius. Okay, so very, very simple data set. It's very small, so running any model should be relatively quick, right? Now, one question I want to pose you, right? Why did we actually choose to predict the bulk modulus using these features? Is there a good reason why I believe that there will be a relationship between them? Anyone? Let's start with the melting point and boiling point. Why do we believe that there should be a relationship between melting point and boiling point and the bulk modulus? What happens when you melt a material?
Sorry,
what happens when you melt a material? Okay. What's the difference between a liquid and a solid?
Packing.
Yeah. So essentially, when you melt a material, you are essentially semi-breaking the bonds between the atoms. Okay. And the strength of the bond between the atoms is also related to how what the bulk modulus of a material, right? The bulk modulus of a material is basically when you apply a pressure on the material, how much does the volume change? That is given. That's actually also a measurement of the bond strength. Okay, so things like melting point and boiling point, we have some reasonable. It's a reasonable assumption that they are essentially related to the bonding strength of the between the atoms. And the bulk modulus is also related to the bond strength between the atoms. Okay. Now, there's no good reason to use atomic number. Okay, I'm throwing it in there just as a more or less irrelevant variable. Electronegativity, again, this is a variable that is a measurement of how likely a element gives up its electron, right? So it actually is also related to the bond strength. And atomic radius is also, the bigger the atom, the weaker it tends to be. And again, that's also related to the bond strength. Okay? So these are the reasons why we actually chose, I gave this set of variables to try to predict the bulk modulus, right? So the moral of the story here is that just because you are using a machine learning model to predict a property doesn't mean that you don't need to understand material science, okay? You have to always start from some hypothesis of what features are going to be related to the target that you are going to try to predict, okay? So there is also a question that you always have to remember when you are reading papers on machine learning or literature on machine learning out there, right? Because very frequently, people like to throw in all kinds of variables into their models, right? So for example, things like atomic number. Why would the atomic number have any relation to the bulk modulus of a material, right? I mean, I don't know of any relationship between the atomic number and the bulk modulus, okay? So this is the kind of questions that you should be asking, right? And remember that the more features you throw into a problem, the harder it is for the machine learning model to figure out which features matter and which features do not matter, right? So you should always try to start from a sensible size number of features, and ideally you want the features to be as physically relevant and as non-correlated with each other as possible, okay? All right. Now, other than just the variables themselves, we are also going to throw in some transformations of inputs, okay? The reason is because, first of all, I want to demonstrate application of the linear model beyond just your simple linear regression of these variables, okay? So I'm going to add things like the square and square root of the electronegativity and the atomic radius into the mix, just to show you how that works and how you can actually use pandas to actually manipulate all these variables very quickly, okay? All right. So this is the code. I'm going to go to the Jupyter notebook in a short while, okay? So the package that we are using is pandas, okay? So pandas, as a reiteration, pandas basically creates objects called data frames, which are essentially a two-dimensional data set object, okay? You can think of it like an Excel spreadsheet, which is precisely what you see in the previous slide, okay? So they have very useful functions, like you just do, I'm importing pandas as PD, which is very, by convention, a lot of people do that in the literature. So there is this function called read CSV. CSV stands for comma separated values, okay? And you just read the data. I'm going to set the index column to be 0, which means, in other words, I'm going to make the element names essentially my indexes in this index, yes?
So the element data that you imported, was that from like an Excel file that you downloaded as a CSV?
No, I created the Excel file myself. So I created the CSV file myself. Oh, okay. So, but essentially an Excel and CSV are almost the same. Okay. Yeah. You can save an Excel file as a CSV, but you can also use pandas to directly read an Excel file. So either one works, yes.
And I noticed that you imported the CSV from not from anything, so I was wondering where did you fetch it from? Like,
yeah, I'm going to go to that soon, okay? So later I'm going to show you what that data set looks like, and then I'm going to talk about how we actually create the additional transformations of data points. Here we are doing it manually. At a later part in the course, I'm going to show you how you can use scikit-learn to actually do this kind of polynomial transformations, okay? And then we are going to set up our x and y, and then we are going to do our machine learning model, okay? All right. Once I get to the Jupyter notebook, you will see this, okay? Now, in scikit-learn, all the linear models, which includes both your standard multiple linear regression model as well as subsequently, later in this lecture, we are going to talk about how we extend linear models. All those models are in this sub-package called linear model, okay? Very obvious, right? So in scikit-learn, the package linear model, under the linear model package, there is linear regression. And then essentially what you do to fit the model is you just call the function called fit, okay? You give it your x, which is your features, and y, which is your targets. And then that will fit your linear regression model, and then you can basically get the coefficients and the intercept over here, okay? Now, one of the things to note about using scikit-learn for linear regression is that your x should only contain the features. So even though when we show you the matrix, there's a 1 column in front, there's no need to add that column when you are actually using scikit-learn to do multiple linear regression, because they automatically add that intercept column, okay? By default, the fit intercept parameter in linear regression is true. In other words, it will assume that you want to fit an intercept. you can also do a multiple linear regression without an intercept. In other words, you assume that your beta naught is set to 0. Okay, that is also another kind of multiple linear regression model. Okay, all right. So let me go to the documentation first because I think that's quite useful. So this is the scikit-learn multiple linear regression documentation. Okay, this is basically one of the simplest models in scikit-learn, right? You see that there aren't really any parameters you have to give it, right? There's hardly anything you need to define for a multiple linear regression model. The only thing you need to define is, well, do I want an intercept or not, right? The rest doesn't really make all that much difference. Copy X just means, do I want to copy in my feature matrix so that when I make any modifications to it, it's not going to affect the original data. N jobs is for if you want to parallelize the fitting of the code across multiple CPUs. Okay, so this is a useful parameter if you are fitting a very large model. I have never found a need to use it when I'm doing a multiple linear regression because there's generally that doesn't help. Okay, for multiple linear regression, for the more complex models, N jobs is actually a useful parameter to use. Okay, and the rest we are not going to care about. Okay, and the other thing that you need to know when you are reading the documentation of something like scikit-learn is these attributes, right? Attributes tell you that what are some the linear regression object, what are some of the attributes that you will have in that object, and what do those attributes give you, right? So you notice that there is this COEF underscore. So this, of course, are the coefficients. So after you call the fit method, you will have this attribute, and then you can basically find the coefficients of your model. Okay. There's also things like a rank variable, which tells you what's the rank of your input matrix, the number of features, what are some of the names of the features. So if you actually give it a pandas data frame, it actually will have the names of your input feature in there. Okay. And so on and so forth. Okay, so I'm going to, and also there's an intercept term. Okay, so the intercept gives you of course, the intercept of your multiple linear regression. All right. All right. Now, the other thing I want you to note about the scikit-learn linear model is if you click on here, you see that scikit-learn. So let me go to the API reference first. Right. So in scikit-learn, if you look at the documentation. They have a lot of sub-packages. Base basically defines all the base mixing classes. By and large, for you, you don't really need to care about these. These are more for model developers like myself. Okay, for people who are using the models, what you really care about is basically everything that comes after it. Things like there are packages for calibration. Packages for clustering. I'm going to come back to this later in a later part of the lecture. There are data sets that comes built in with scikit-learn. These are useful for actual playing around with scikit-learn in itself. Okay. There is, let me go to the one that matters for now, which is your linear models. Okay. So if you go to linear, you will see that under the linear model package, okay, there are all these different kinds of linear models, right? Now, there are two types of models. There are classifiers and there are regressors, okay? Classifier means that these are models that give you a classification, they are meant to solve a classification problem, right? Regressors means these are meant to solve a regression problem. Now, what is a classification problem and what's a regression problem? A regression problem is something where you actually want to predict a specific value for something, right? Like, for example, I want to predict the bulk modulus. So when I want to predict a bulk modulus, I want to predict, is the bulk modulus 200, or is it 201, or is it 202, or is it 100, right? When I'm doing a classification, this is a different kind of problem. A classification, you are trying to predict a category. So for instance, I want to predict whether a material is a metal or insulator. That's called a classification problem. All right. So these are linear models for classification. We are going to come back to these later. But right now we are using this, okay, which are our linear regressors. And if you look at the linear regressors, there's the very standard ordinary least squares linear regression. You will see the ridge regression in a little bit, okay? And there are some other regressors with variable selection. Again, you are going to see this in a little bit. The one that we will play around with a little bit is called lasso, okay? And all these are different kinds of linear regression models that you can use, okay? All right. With that, let me go back to my Google Colab. Okay, so this is the lecture number 3 notebook. Okay, so in linear methods, I'm going to make some imports first. Panda, Seaborn, and NumPy. These are always packages that I always use. Matplotlib is just for plotting the data, and I like to set some of the parameters for Matplotlib because by default, Matplotlib gives you graphs that have very small fonts, okay? And I'm quite old already. I can't actually read the fonts anymore. So I like to set a certain default figure size, and I like to set big fonts for all my X labels and Y labels, okay? So that I can read them more easily, right? Now, so let me run this first, okay? And just now, one of you actually asked, where do I load the data from, right? Now, the read CSV method, the beauty of it is that you can actually give it a direct file name, or you can also give it a URL, right? And when you give it a URL, it will automatically know that I need to download that data from that URL and then load it, okay? So this is the full URL for the element data.csv file, okay? It is essentially in the GitHub repo under the lectures notebook directory, all right? So this is the full URL. So when you are doing loading of data from Figshare in your lab number 1, this is what you should be using, okay? All right, so I'm going to read my CSV file from that URL. I'm setting my index column to 0, and I'm going to just print the data, okay? And this is basically the entire data set, right? So you can see that my index column is just the symbol of the element. My bulk modulus is in the K column. This is my melting point, boiling point, my atomic number, right? My electronegativity, and my atomic radius, okay? So all these data are given to you, right? So if you actually go to the file itself, this is what the file looks like, okay? Very, very simple, right? And you open, by default, when you double click a CSV file, it will open in Excel, but it is actually a text file, okay? I can show you if I open this in Sublime Text. This is actually what a comma separated value file looks like. Essentially, as its name implies, it's just a set of values with comma separating all of them, okay? All right, so this is, I generally prefer this kind of very simple text formats over complicated formats like Excel, okay? Because usually there's no good reason for me to be using Excel, right? Now, you notice that there are 83 rows and 6 columns. 83 rows, those are the number of elements that are in this data set. It is essentially almost all the elements in the periodic table, excluding, I think, a few radioactive elements here and there for which we don't have bulk modulus data, okay? 6 columns, basically the target itself plus 5 different features, okay? Now, whenever you do, we are also going to, what we want to do is also to, remember we wanted to add some transformations of variables to our initial set of features, right? So we don't just want to use x, we also want to add x squared and square root of x, in other words, the square of the electronegativity and the square root of the electronegativity to our feature set, right? Now, there's a very simple way you can do this, right? So you can just say, well, I'm going to create a new column. So this basically says, I am going to create a new column called x to the power of 2. And that new column is given by my x column raised to the power of 2, right? Similarly, I'm creating a square root x column, and that's basically my x column to the power of 0.5, which is the square root. And similarly, I do that for r, okay, which is my atomic radius, okay. And basically, what you get is this new data frame. So all you need to do is those 4 very simple one-line commands, and you basically get now an expanded data frame, which includes not just your original 6 columns, but also these 4 additional columns, which has your x squared, square root x, r squared, and square root r in additional columns. Okay? All right. Now, the next step is to basically initialize our linear regression model and to fit the linear regression model to our input and output, right? Now, for us, what we want to do is to first get our features and also our target, right? Remember, our target is the bulk modulus, which is k, right? So the easy one, I'm going to set y as my target. Target is just equals to data k, which means this is the k column in my data frame. For my x column, which I want to basically get all the other columns except k, so I'm going to use this least comprehension, which I basically go through all the columns in my data in my data frame, and I'm going to basically say that my features are all the columns except the k column, right? So if the column name is k, I'm going to exclude that, right? And with that, I actually create my x and y, okay? So let me show you how this works. I'm going to print x. I'm going to add a print x and print y here so that you can see what they look like, okay? So, so this is my x. My x is essentially my data frame. Now you notice that there's no k column now, right? So there are 9 features, 9 columns. In other words, there are 9 features in total that I'm going to use. And then my target y is just my k column, which is my bulk modulus, okay? All right. Now, we are going to now do our multiple linear regression, okay? So, I'm going to import the linear model package from scikit-learn. I'm going to initialize the model, which is the linear regression class. I'm going to run regression.fit, and I'm going to give it my features, and I'm going to give it my target, okay? And then I'm going to ask it to run a score. By default, the score is the r square of the training data, okay? And I wrote this to actually print out the regression equation that is the final fit, okay, and including the intercept as well, okay? And then I'm also going to plot out the actual predictions versus the actual the original data set, okay? So over here, let me run this code, and this is the result, okay? So after running the linear regression, this is the linear regression equation that the model came up with. Basically, the optimized parameter says that the bulk modulus is equals to an intercept of negative 243.8 plus a coefficient of 4.25 times 10 to the power minus 2 times the melting point plus 2.76 times 10 to the power minus 2 times the boiling point, and so on and so forth, okay? And the actual predicted versus the bulk modulus, the original bulk modulus is on the x-axis and the predicted bulk modulus is on the y-axis, is shown right here, okay? So what you will see is that, well, I mean, the model isn't that good, obviously. See, this is a very simple model, right? I only have 6 variables and the model isn't particularly complicated. So it does seem that my R square, there is some correlation. In other words, that my predictor values are in general the right trend, in the sense that if I predict a higher bulk modulus, that material actually tends to have a higher bulk modulus than my another material. But the error is not that low. The R square is also not particularly high, right? So this model is reasonable, but not exactly state of the art, right? Okay. Any questions regarding this code example? No? Okay. Let me continue on. Okay, so before we continue on, I just want to highlight a few things. Now, even though it seems that this model performs reasonably, I want to be very clear that this shouldn't be how you actually fit a machine learning model, right? What you are doing here is that you are just taking the entire data set that you have and you are throwing it into your machine learning model. And then you fit, and then you conclude, well, this is the error on my training data, and this is how well it performs. That is actually not how you should evaluate a machine learning model. Whenever you want to fit a machine learning model, you always need to take your original data set, you need to split it into a training set, and you split it into a test set, and then you only train using the subset of data called the training set, and then you check how well does your model perform on the test set, okay? So later I'm going to talk about how you go about doing that. We can use something called cross-validation to actually properly evaluate the performance of our multiple linear regression model on this data set, okay? All right. Now, very often, after you have fitted your linear regression model, you always want to know, well, which of the coefficients actually indicate that that particular variable matters, right? For instance, is it the melting point that is the most important for predicting my bulk modulus, or is it the boiling point, or is it some other variable, right? So if we make the assumption that our errors in y follow a standard normal distribution, okay, and the errors in our coefficients, the fitted coefficients, are also follows a Gaussian distribution, you can actually carry out a hypothesis testing to check whether a beta j is significantly greater than 0 or not, okay? So that hypothesis testing is governed by this t statistic, okay? So I'm assuming you know what a hypothesis testing is and what's a t statistic, okay? So that t statistic is given by your beta j predicted divided by the sigma, which is the estimated variance of your target, square root of v of j, okay? And v of j is basically the diagonal element in this matrix over here, right? So this has a t distribution with m minus p minus 1 degrees of freedom. So you can look up your student's t distribution table, and then you can do a proper hypothesis testing, say, for example, at the 95% level or the 99% level, to check whether that particular beta coefficient is significantly greater than 0 or not, okay? So that's one way of determining whether any of your coefficients is significantly greater than 0, all right? Now, but also, more often than not, you actually do not just want to test whether each individual beta coefficient is greater than 0. You sometimes want to test whether a set of coefficients or a set of features are significant, right? So, for example, you may actually have a set of coefficients that are related to the k levels of a categorical variable, right? Now, in that instance, you actually need to use the F statistic, okay? So the F statistic is given by the residual sum of squares with all the parameters minus the residual sum of the squares for the smaller model, where you actually take out the entire set of categorical variables, divided by P1 minus P0, which is basically the total number of parameters in each model. And essentially with this formula, you can actually run a F statistic test to check whether that entire set of categorical variables actually matters in the prediction of your final target. Okay? All right. Now, there's something called the Gauss Markov theorem. Okay, so if we look at the mean square error of an estimator, okay, so the mean square error of an estimator theta, okay, is given by the expectation of the estimator minus the variable itself squared. Okay, now if you expand this out, okay, you will find that you can write it as basically the variance of the estimator itself plus the expected value of the estimator minus the variable itself squared, right? So this is actually quite easily demonstrated. You just expand this theta hat minus theta squared, okay, and you basically can get this expression over here. Now, so what does this mean, right? This means that the mean square error for an estimator can be broken down into two components, right? The variance of the estimator itself, okay, and the square of this thing, and this thing is called the bias, okay. It is essentially the square of the differences between the average of the estimator versus the actual variable itself, okay. So we are going to come back to this thing because this actually matters when we try to work on further extensions of the linear model beyond just your simple least squares regression, right? Now, what the Gauss Markov theorem states basically is that for unbiased estimators, in other words, for estimators where your your expectation of your estimator minus the variable itself is 0, so that's called an unbiased estimator. The least squares estimator always has the smallest variance, okay? So in other words, if you want your estimator to be an unbiased one, then the least square solution is basically the best thing that you can do, okay? So that's the best solution in terms of your minimum sum of mean square error. However, if you have an estimator that is biased, okay, and that's what happens when we actually introduce extensions beyond your standard multiple linear regression, what you are going to do is that you are going to allow there to be some bias. In other words, you allow this to increase, but then you can actually achieve a lower total mean square error by decreasing your variance in your estimator, okay? So this is what we are going to touch on that in a short while, okay? All right. Now, at this point, it is a good time to start talking about a little bit about what are some of the best practices when you go about fitting a machine learning model, right? Now, so far, I've shown you a very simple example. I took in the entire data set, I've broken it up into features and targets, and then I threw the entire data set into my machine learning model, and I called the function called fit, and whoa, I have a prediction, okay? Now, that is not how you should be actually doing it, right? So this part, I'm going to talk about how you actually should be doing model selection, and we are going to apply this rigorously to all the machine learning models that we are going to fit from this point forward, okay? Now, so here we are going to talk about model assessment and model selection, right? And what is model selection, right? Whenever we want to assess and select models, we want to have a measure of the performance of the model, right? Now, whenever we talk about the performance of a model, the performance of the model is always measured on independent test data, okay? In other words, it must be measured on data that the model itself has not seen during the training process, okay? if you use training data to test the model, that is not a valid assessment of the performance of the model. Okay? So you are always not allowed to simply provide the model metrics based on training data alone, right? I would say that if you do that, that immediately that calls into question the reliability of your model. Okay, so here we are going to limit ourselves to fairly high-level concepts, and as and when we get into the later lectures, you will see us coming back to all these concepts over and over again with practical examples, right? All right, so first let us decide what are some of the ways in which we can calculate the error of a model, right? So this is some of the loss functions that we always use, okay? So these two are the most typical, especially for regression models. There is the mean square error and there's the mean absolute error, right? We have already seen the mean square error. The mean square error is basically the error of your observations minus the predicted observation, predicted value squared, and then you sum all the squares, okay? The mean absolute error is a little bit similar to the mean square error. However, instead of squaring this difference, you just take the absolute value of our observations versus the predictions, and then you sum all the absolute values, okay? So this is called the mean absolute error, right? Now, regardless of whether you are using mean square error or mean absolute error, you have two kinds of losses, okay? One is called the test loss. The test loss is essentially the value of your loss function over your independent test set. And then you also have your training loss, which is the value of your loss function over your training set, okay? All right. Now, this shows you, this is actually a very useful graph, okay? It basically shows you what happens when you increase the model complexity, right? So, this graph basically shows you the what happens to your training and test errors as you keep increasing the model complexity. Now, what is model complexity? Model complexity as a rough concept is basically the total number of parameters that you are fitting, right? So in a multiple linear regression model, this has a very intuitive meaning. It just means how many features am I using in my multiple linear regression model? Am I fitting to one variable? Am I fitting to 5 variables? Am I fitting to 100 variables? Okay. So as you increase the number of variables that you're fitting, you are increasing your model complexity. Now, when we look at other machine learning models, there are also corollaries to this model complexity concept, right? Now, one of the things that you should always know is that training errors always decrease with increasing model complexity, okay? What this means is that if I can fit the multiple linear regression model using three variables, if I add a fourth variable, the training error can only decrease or stay the same, okay? So you may be lulled into a very false sense of security, right? Like, oh, I have fitted with 3 variables, my training error is X, and once I added in another 8 variables, my training error is now close to 0, right? So, and you happily think that your model is actually improving, right? Now, test errors, however, which is what actually matters, does not have a monotonic decreasing relationship with model complexity. So, in other words, as you add more and more variables, your test error do not actually always decrease, okay? So this is generally what happens when you plot the training and test errors with respect to the model complexity. You see that your training error just keeps decreasing and decreasing and decreasing. Of course, the rate of decrease will slow down, but it will keep decreasing. However, your test error actually have this kind of relationship. There is always some point where essentially as you increase the model complexity, you are doing worse, okay? So in other words, by adding one more variable, your test performance actually decreases. In other words, your model performance is actually worse, all right? Now, this is basically a classic example of underfitting and overfitting, right? So the lowest test error is basically, we can consider it somewhat as the optimal point, right? This is the, given the structure of the model, this is basically the best possible model I can use, okay? And if I go fewer parameters, I am essentially underfitting. In other words, I do not have enough variables to actually describe my target properly, okay? I do not have enough features to describe my target properly, right? If I actually go higher in terms of model complexity, that means I'm using too many features or too many parameters to describe that relationship, and I'm in essence overfitting. I'm fitting to whatever noise there is in the training data, and because I'm fitting to the noise, I'm actually getting worse results on my test data. Okay, so again, this is an extremely important concept. Okay, so you always need to evaluate your model performance on your test data, and that actually there is some optimal somewhere of your hyperparameters that minimizes that test error. Okay. All right. Now, so what do we do when we actually have a data set? Basically, there are two steps that we always need to take. One is called model selection, and one is called model assessment. Model selection just means that whenever I have a specific type of model, let's say a multiple linear regression model, or there's a rich regression model or some other model, I want to choose the model between the different types of model that actually gives me the best model. I want to choose the best model between all those different types of models that I'm selecting in between. That's called model selection. Okay. Now, model assessment is what happens after that. Okay. Model assessment is basically, well, I have already selected my best model. I want to be able to tell the person who is going to use my model, this is how well I expect it to perform. Okay. And for that, I actually calculate the prediction error over new data. So in other words, I need a completely set of different data to actually estimate my generalization error. Okay. So if you have lots and lots of data, it is very simple. Okay. You divide the data into three parts. You have a training set, which is what you use to fit the model. You have a validation set, which you use to estimate the prediction error, such that you can select which of the models are which model is the best. And then you finally have a test set, which you then say, well, this is the error on the test set, and this is my expected performance of my model. Okay. Now, when we do this kind of training validation test split, you need some ratio. Typically, what we do is that we take about 50% of the data to be my training data, 25% to be my validation data, and 25% to be my test data. More commonly, you also use something like 80-10-10, which is 80% training data, 10% validation data, and 10% test data. And of course, if you have very, very little data, in other words, you just don't have enough data to even train the model properly, you may sometimes go for something like 90-5-5. Okay. Now, one thing that is important to note is that at no point during the model fitting process should your test set be seen. So in other words, once you have done your training, validation, test split, your test data, you are not allowed to use your test data for anything. You can't use it to select models. You can't use it to do anything. It should be set aside, and only when you actually have your final model, then you actually use your test set to evaluate its performance. Okay. Now, one way to actually get a better estimate of your model performance to do model selection is doing what is called k-fold cross validation. Okay. So this is usually the simplest and probably the most widely used approach to actually validate models, okay? The concept is actually fairly simple, right? So what you do is that you take your data set, the one that you are going to use for training and validation. You split it into k buckets, okay? Typically, you split that k buckets by random, okay? Typically, that k is usually 5 to 10, roughly speaking. Most often, you will see, well, people just say 5-fold cross-validation, 10-fold cross-validation. There is also what is called leave one out cross-validation, which in other words means that I'm going to take my entire data set except for one data point as my training data, and that one data point is my single validation piece data, okay? That's why it's called leave one out cross-validation, right? So here I show you the example of what is 5-fold cross-validation. So I'm splitting my data into 5 sets, okay? I'm going to first say, well, I'm going to take one of the data set as my validation set. The other 4 are my training data. I'm going to train my model using these 4 buckets of data. And then I'm going to use this one validation bucket to actually measure the model performance, okay? Now, once I calculate that validation data error, I'm going to now choose a different bucket as my validation data and the other 4 buckets as my training data, and I'm going to repeat that process. So in other words, I'm going to do that 5 times, okay? Each time I'm going to select, first I'm going to select this one as my validation data, then I'm going to select the next bucket as my validation data, then the next bucket, and the next bucket, and the next bucket. And then I'm going to have 5 different models fitted and 5 different validation errors. And then I'm going to take the average of all the validation errors, and that's basically my cross-validation score, okay? So ignore this complicated formula. It's basically just the average of your 5 losses from your 5 different models, okay? And once we have done that, then we can choose the set of parameters that give me the lowest cross-validation score, okay? All right. Now, you can actually do all this in scikit-learn quite easily. So I'm sure most of you don't want to actually have to manually go and split the data into 5 buckets and individually split them. So in scikit-learn, cross-validation is in the model selection package. Under the model selection package, there is cross-validate and there's k-fold. The reason why you would need to actually use k-fold is because by default, scikit-learn doesn't shuffle the data, okay? So in other words, when they do the splitting, they will just assume that the data is already randomized. So I generally prefer to make sure that they actually shuffle the input data so that they can do the split, okay? So k-fold, the variables, the input arguments are quite simple. N splits means the total number of splits. 5 means 5-fold cross-validation. I shuffle. Typically, you should set a random seed. The random seed just basically initializes the random generator for your shuffling. The reason why you do this is to make sure that when you run that code today and tomorrow, you get repeatable results, right? Because sometimes, because of the random generation process, you can actually get different results when you do different runs. By setting the random seed, you are guaranteeing that you always get the same results every single time, okay? Now, and then the cross-validate methods just basically runs a cross-validation on, say, the model. Here I'm using a ridge regression, which we are going to come to later. The input features, here is Z, and the target Y, and you give it the cross-validator, which is our k-fold, and then you then it automatically gives you your cross-validation score, okay? All right. So just to show you the documentation, so this is our cross-validate method. You see that basically you need to give it an estimator. So in scikit-learn, all the models are called estimators. In other words, they perform an estimation, okay? As per normal, you need to give it the input feature matrix X, and if you are doing an actual supervised learning, you need to give it the model, the target Y. If you are doing an unsupervised learning, which we are going to come to, Y is optional, okay? And then there's a CV. CV basically spells out what kind of cross-validation you are doing. if you just put the number 5, it means 5-fold cross-validation, but because we want to do shuffling as well, we use k-fold, okay? Okay. Okay, let me go back to my example. Now, inside scikit-learn, besides the cross-validate method, there is also this method called train test split. So this is a very useful method to basically split your data into training and test set. So train test split, you basically tell them, you give it your x and y, okay? That's my original x and y. You tell them what you want your test data size to be. So here I give it 0.1. 0.1 means I'm going to select 10% of my data as my test set, okay? And then random state again is a random the seed for the random number generator. So just to show you what this does, okay? So remember our original data set has 83 data points, right? So basically what this train test split method does is that it takes your x and y, it splits into an training data x, test data x, training data y, training data y, and the test y, okay? Now, the first one is our x training data, and you see that instead of 83 rows, there is now 74 rows. In other words, this is 90% of the original data set, okay? And our test data has only 9 elements, I think. Yep. So there's for our test data, we have just 9 different data points. Okay. So this gives me a training and test set that I can use to then fit our model. Okay. All right. Now, okay, I don't want to rush through this, so I'm going to come to this in our next lecture, where I'm going to talk about, instead of doing what we did previously, which is to just throw in the entire data set to train our linear regression model, what we really should have done is to basically do a proper cross-validation method to train the model to get a cross-validated prediction performance. Okay, when we talk about measuring model performance, there are a few metrics that you will see very often in the literature. Okay, so we have gone through 2 of them. One is called the mean squared error, and the other one is called the mean absolute error. Okay, so the mean squared error is basically you take each observation, you minus the prediction, and then you square that difference between them, okay, and then you sum over all the observations that you have and you divide by the total number of observations, okay. So that is why it is called a mean squared error, okay. So the mean absolute error is somewhat like the mean squared error. The only difference is that instead of squaring the difference, you take the absolute of the difference, and then you sum over all the absolutes of the differences, and then you divide by the total number of observation, okay. So just to use the correct terminology, both the mean square error and the mean absolute error are what are called loss functions. Okay, loss functions are essentially a function that you minimize to get the best possible solution or the best possible model. Okay, so you either minimize the mean square error, which is the most common, or you sometimes minimize the mean absolute error. Okay, now whenever we measure a model, we always split the data into training and test data. Okay, so you only use training data to train your model, and you evaluate your model on test data. So whenever we report errors, we always need to report training error. We also need to report test error, right? And those are basically, well, the training error is just the value of your loss function over the training set, and your test error is the value of your loss function over the independent test set. Okay. Now, as I mentioned before, one of the things that you need to be aware of is that training and test errors have very different behavior with model complexity, okay? So whenever we talk about model complexity, that essentially just means the, as a rough rule of thumb, is basically the total number of parameters in your model that you're fitting to. So for instance, in our multiple linear regression model, that can mean, well, am I using 3 variables or am I using 10 variables? Am I adding the square of the variables or into my fit and that sort of thing, right? So one thing to always remember is that as you increase the model complexity, training errors always decrease, okay? So if you can, for example, if you can fit a set of data points to a straight line, you can always fit the same set of data points to a power 2 polynomial, and your training error will either decrease or stay the same, okay? However, test errors do not have a monotonic relationship with model complexity, right? So because the test errors are never used to train the model, so if you plot basically your test errors as a function of model complexity, there's usually a minimum somewhere. There's an optimum value for the model complexity. In other words, you should be having a model, in this case, in this particular example that you see here, the optimal model complexity is about 20 something, okay? You shouldn't have a model complexity that is 5, and you shouldn't have a model complexity that is 35, right? So when you actually have too low a model complexity, essentially you are underfitting the data. So you have very, very low variance, but you have very high bias. In other words, your model is too rigid, right? You can't actually fit the data properly. If you have too high a model complexity, you're overfitting the data. So what this means is that your bias is very low. You're making very few assumptions about the structure of your data, but because you're making too few assumptions about it, the extrapolability of your model becomes much worse. Okay, so in other words, you have very high variance, right? Now, since the last lecture, I decided to add one more slide to show you what underfitting and overfitting really means. Okay, so this is actually something I got from the MathWorks website. Okay, there's two kinds of machine learning problems that you can think of, classification and regression. So these are examples of overfitting, having the right fit, and underfitting, right? So let's say you have a set of experimental measurements, and the experimental measurements are all your yellow circles over here, right? Now you look at that yellow circles, you think, oh well, okay. If I draw this line, it seems that it is a pretty good fit, right? It does seem like that it's a quasi quadratic x square kind of fit, right? Now, if you choose to only fit the data to a linear model, in other words, you just choose y equals to mx plus c, you can still fit the data, right? But you are not really getting the best test error, because what is happening is that using this rigid fit, you are in essence not able to model the true relationship between your y and x, right? Now, you can also do the reverse. Let's say you decide that I'm not happy with just a polynomial fit. I'm going to introduce x to the power 4, x to the power 5, x to the power 10 terms. And when you do the fit, the blue line is basically what you get, right? In other words, the model tries its best to fit to all the available data that is present in the training set, right? Now, this model, you will get a very low training error, right? Because now most of the points are somewhat close to the line, but you are also fitting to the noise in the data, right? So there's the spread around this line is probably just noise, right? For example, when you do an experimental measurement, there can be noise in the data, right? So this fit will give you a very low training error, but if you try to use this fit to make predictions, the result is going to be a very high test error because it is overfitting the data, okay? Now, similarly, if you look at this classification problem, let's say you just want to split the data between the blue and the orange region, you can see that, well, probably the correct split is via this line. Now, if you have a simple linear fit, you basically will draw a line through here. But if you have a very, very complicated fit, you essentially will try to navigate your way around all the points that are on either side. And so basically, again, this is underfitting, this is overfitting, and there is a right middle in which you get the lowest test errors. Okay. All right. Now, I talked about model selection versus model assessment. Okay, so just recap that whenever we do model selection, we are essentially trying to compare different types of different models to choose the best one. Now, different models mean anything from just having different parameters for the same type of model. So for example, you can have different multiple linear regression models, but with different features, that's considered different models. Or it can also be completely different models, like one is a multiple linear regression model, one is a neural network, one is a random forest model, or other ensemble models, and so on and so forth. Okay, so selecting the best model, regardless of how you define the best model, that's called model selection. All right. Model assessment is basically what you do at the end, right? So after you have selected, well, this is my best model from all the ones that I've trained. You want to give it to someone else to use it, and you want to give them some uncertainty estimate. So you want to say, well, this is my model for, say, the band gap of a material, and you want to tell them, well, the error is about plus minus 0.x. So the way that you do that is to basically use data that has never been seen before, and then you use your best model on it, and then calculate the prediction error, and that is basically your prediction error. Okay. Now, so whenever you have a complete data set, typically the way that you do this is to split the data into training and validation sets, and as well as a test set. Okay. So very commonly in the literature, you see people use like 80-10-10. So they will take 80% of the total data set as a training data, 10% as your validation data, and finally in the last 10% is your test data. Okay. Now, one way to make better use of your data is to do what is called cross-validation. In other words, instead of just splitting your data once and taking 80-10-10 split, you can also split your data into different buckets, right? So you basically take your data and you, for example, you split it into 5 buckets, and you choose one of the bucket as your validation data, and you use the other 4 buckets as your training data, and then you repeat that process over every single bucket, right? And then once you do that, you take the average of the validation scores on all the parameters, and that basically gives you an averaged model score. So this is a more robust way of comparing different models. Okay. So as I mentioned, in scikit-learn, there are already a lot of tools to help you do this. You can do under the model selection package. There's actually a cross-validate method, and there's also a K4 method. So you do have to use the K4 method, and because we want to shuffle the data usually, and also it's useful to initialize the random states so that you have consistent reproducible results when you actually do model fitting. Okay. All right. I think there's a question in the chat. Let me see. Is there an ideal way to separate the data into training and validation data, or should it be random? Okay, so there are many ways of separating the data into training and validation data. So it all depends on what kind of data you're working with. Okay, so let me give you an example, right? So for materials data, typically we just do random, right? But there are instances where you want some randomness, but not completely random, right? So let's say you have a set of data, you know that half of the data is on metals and half of the data is insulators, and you want to do an 80-10 split. Now, one of the things that you wouldn't want to do is to say, I select all the metal data and a little bit of the insulator data, and only the insulator data is the test set, right? So that's a split that you wouldn't want to do. Now, if you do a random, you probably would get roughly an 80-20 split anyway, but sometimes you want to do what is called stratified sampling. So in other words, you will take the metal data, you do a 80-20 split, and then you take the insulated data and you do a 80-20 split, and then you then use that the 80% of each category as your training data, and you use the 20% of each category as your test data. So there are different approaches to ensure this kind of a good split, right? The other way that I would the other example that I will give you is, for instance, when you want to say sample the population to understand, say, the preference for American president, right, before the presidential elections. Okay, so you will see that you will never want to sample just one part of the country or one specific ethnic group or one specific group of any specific homogeneous group of people, right? So for instance, if you say I'm going to sample the results of the presidential election, I'm only going to sample California. Well, that's not going to give you a very accurate reproduction of the American electorate, right? So that's why whenever people do sampling for the elections, you do want to make sure that you create a reflective sample of your data set, right? So which is the whole American population, right? So this is so in machine learning models, it is the same. You want to sample things diversely so that you actually do get a good representation of the underlying space that you're going to work with. Okay, so yeah. Any other questions? All right. Now, before we proceed further, I want to show you some of the characteristics of the example materials data set. So using Seaborn, you can actually plot the correlations between each of the features. So for example, the melting point, the boiling point. So we already have all the features, right? So just a recap, our data set contains the features contain the melting point, boiling point, atomic number, the electronegativity and the atomic radius, and we also added the square of the atomic number, the electronegativity and the square root of the electronegativity, as well as the square of the atomic radius and the square root of the atomic radius, right? Now, so you can plot this kind of correlation plots, which basically, for example, plots the correlation between the melting point and the boiling point, the melting point and the atomic number, and so on and so forth. And you can see that quite clearly there's very strong correlation between some of the features, right? So for instance, melting point and boiling point, well, it's not a surprise, right? The higher the melting point, the higher the boiling point, right? So it does seem that there's a very strong correlation between them. But there is also correlation between other set of variables that you may not think about, right? So even, for example, if you look at the melting point and things like the electronegativity and atomic radius, you do see that there is some relationship. It's not as clear as the melting point and boiling point, right? So, but the correlation is definitely not zero, okay? Now, so another way to visualize this is using this kind of heat map, okay? This shows you essentially whether the what the correlations are. Of course, the redder it is, the higher the correlation. Negative correlation is basically the bluer it is, and neutral ones are closer to gray and white, okay? And you can see that a lot of the features are quite highly correlated with one another. So in other words, you have redundant features, right? So you may want to actually not choose all the input features that we have initially selected. So in other words, we need to figure out which subset of input features would actually be useful, be useful for making the prediction of the bulk modulus. Okay. All right. So so far we have already talked about the loss functions for regression. We have our bulk modulus, and sorry, we have our squared loss, and we also have our mean absolute error. Those are the two most common loss functions. Now, one thing you need to keep in mind is, well, which one should I choose, right? So this is a very common question that people have whenever they are trying to select loss functions for model fitting, right? So the properties are very from the mathematical formulation of the loss functions, you can already tell what are the relative pros and cons of both, right? So the mean square error, because you are squaring any error, basically what mean square error does is that it heavily penalizes outliers with large observed residuals, right? So in other words, using mean square error is less robust to data with very long-tailed distributions. So in other words, if you have a lot of data that is sitting in the extrema of your distribution, what will happen is that mean square error would think that those errors are very, very large, and when you are trying to fit the model, they will try to minimize those very big residuals. The model will try to focus on minimizing those very big errors, right? So this is why mean square error is less robust to outliers, right? Mean absolute error, because there isn't this square term, so basically it is more robust against outliers. There are also other criteria that people use in regression. So for example, there's this thing called the Huber loss. So in the Huber loss, you basically have essentially the mean square error if the error is less than some threshold that you set, but when the error is larger than that threshold, you basically set it to be closer to something like a mean absolute error. Okay, so that's basically some of the options that you have, right? All right.